Good morning and welcome back to the 5G Hack the Mall channel. First of all, I would like to remind you guys that we are going to have the first round of pitches today at 2 p.m. EEST. But before that, we are going to have two interesting lectures, and the first one is about to start soon. The first lecture is about 5G and IoT, and it will be held by Anna Larmo, the principal researcher of Ericsson. Welcome, Anna.
Thank you, Otso. Thanks, and great to be here today. So, my name is Anna Larmo, and I come from Ericsson. I work at Ericsson Research here in Finland, in the research area Networks. And I'm here today to talk to you about 5G and IoT. Thank you. So, let's get going. So here is a short outline of what we're going to cover today. So I will just say a few words about Ericsson Research, who we are, and then we'll look into 5G. And since the beginning of this week you guys spent already learning about 5G, then we're going to jump very quickly into what is IoT. And then, of course, combining those two. What does 5G do for IoT? And then in the end, we have some example cases of what we've been working at with Ericsson Research with. All right, very quickly about our organization. So Ericsson Research is a worldwide organization with 700 researchers, and more than half of our staff are actually PhDs. We are present in 12 countries and in 4 continents, and we've invented all of the mobile generations, so 2G, 3G, 4G, 5G. Next is, of course, 6G, sometime in the future. We have divided ourselves into 8 different research areas. As I mentioned, I come from the research area Networks, but then we also have people working in different other research areas, such as radio, cloud, AI, devices, security, digital representation, and we have a consumer and industry lab who are working then with the use cases that mobile technology is used for. All right. After this very brief introduction into our organization, I'm just going to talk about 5G. So what is 5G actually? So 5G is basically a communication system that comprises of several parts, such as the radio access network, which I myself have worked with a lot, core network, the terminals, and then there are, of course, aspects that go across the whole system. It's a set of standards. They look like the paper on the slide here. So there's a set of standards available on 3gpp.org, and that is basically a specification that specifies 5G. And you have learned a lot about it already this week, so let's just have a brief look at what it contains. So we have the mobility generations coming from 1G to 5G, and with each generation, new services have been added to the network. So 1G was the first mobile system that we ever had. It was started in the US. Here in the Nordics, we had the NMT system. And very quickly in the 90s, we moved to GSM, then 3G, 4G is what we typically use today, and 5G is coming to the market as we speak. So there are already networks, there are devices. And with 4G, that was kind of the big breakthrough for mobile broadband. So all the apps you use on your phone, right? And with 5G, this is really becoming a platform for networked society and enabling extreme performance. What kind of use cases do we speak about when we speak about 5G use cases that go beyond the mobile broadband? Well, we have several different types of use cases, but in 5G and in IoT, it's really the ones in the middle in this picture that are the key use cases. So we have something called the IoT meters, sensors, which we call massive machine type communication, MTC. Then we can have remote controlled machines, and then there are other more advanced use cases like smart transport, smart infrastructure, and vehicles. So basically the 5G is offering now services that can enable new opportunities and flexibility for something that we never had before. Just a quick overview of the timeline of 5G then. So the first release of new radio, NR, release 15, was completed in 3GPP in June 2018, so 2 years ago. And the second release of NR, release 16, is completed as we speak now in 2020. Now due to the coronavirus, there have been some delays in standardization as our standardization delegates from different companies and from all over the world have not been able to meet face to face. So this has slowed down the process slightly, but anyway, the standard will be completed this year, and then we will move on to work on the next release, release 17, which is then the evolution of NR beyond the current capabilities. What did we have in release 15 then? So there is a very big block here on the bottom now that's called EMBB, that's Enhanced Mobile Broadband. And then we have something called FWA, so that's Fixed Wireless Access. Another interesting part of release 15 is that, so in the first release of 5G, in the first release of new radio already, we had something called IIoT. So this is short for Industrial IoT. This means NR is developing in the IoT frame towards the industrial use cases. Then we have lots of different features. I'll just click them through here. You can see a rough timeline here. This is already from last summer, so things may have changed a bit. But you can see a range of use cases here where the standards people are working with at the moment. So we want to enable this whole set of use cases in 5G. V2X refers to vehicle to X, so vehicle to infrastructure, vehicle to vehicle, and so on. We have public safety. This refers to, for example, nationwide networks for the government officials, for the first responders, and so on. NRMTC refers to machine type communication over the new radio interface. This is there, as you can see, starting from release 17. So the massive machine type communication for 4G is already available, and for LTE, and that is something that we can also use with 5G, but then from release 17 onwards, there will be a specific mode for NR, machine type communication for the massive use cases. Then we have drones coming in and lots of more things later on. Okay, I'll click through and you get all the details of the different features that are there. Okay, let's have a brief look at the release 15 key features. I think here we will be quite short because this is something that you already covered earlier this week, but just as a recap. So the key features are ultra-lean design, multi-antenna support, forward compatibility, wide spectrum range, and low latency. So those are the key features of 5G, of the first version of 5G, release 15. Then we have a few more. LTE-NR coexistence. So this means we can use both 4G and 5G side by side. Network slicing. That's an interesting feature and very good for IoT. So this means that you can create slices across the network that can support different kinds of services. Then we have a modular architecture, DU-CU split, so that means distributed unit, central unit split. So we can split the protocol architecture into different parts of the network. And SBA refers to service-based architecture. And this is something that enables the slicing in a good way. So we can have a service per slice supported. There are different architectural options for deploying 5G networks. The first version The first deployments are typically non-standalone. There we have the LTE network that's already present, that's handling the initial access and mobility features. And then the NR is more like a data rate booster. And then we connect to the EPC, so that's the Evolved Packet Core, which is the core network of 4G. The picture shows how it should work. And the other option, which is maturing as we speak, and I think there will be deployments, if not are already out there, is standalone NR. So later on, we want to do deployments without the LTE existing anchors. And then, of course, the NR network will handle both the initial access and mobility, and then we will connect, instead of the EPC, to the 5G core network, so the 5G CN. That was a short recap now on what is 5G. And now next we're going to go into IoT. So what is IoT actually? So IoT is short for Internet of Things. And what does it actually mean? Well, it means a lot of things. You can have sensors, you can have actuators. Sensors create data that maybe go to the cloud. They go over a communication channel. There might be applications that then use this data, and you can play around with the data. There could be machine learning that works on the data sets and learns some insights from the data. We can apply artificial intelligence. So IoT can be pretty much anything of the above, and I've seen the term being used with all these meanings. So sometimes when people talk about IoT, they mean the sensor. Sometimes when they talk about IoT, they mean the cloud instead. So there is a variety of specifications for IoT. And that's also actually true in very literal sense. So there are several different standards and standardization efforts that have tried to capture what IoT is in many different forums. And there is no consensus on one single standard for IoT. So this is something we have to live with. So for 5G, we have one single standard, but for IoT, we are not in that situation. We have many different standards that serve many different purposes and may or may not be used together, and this is the reality for IoT, basically. So the Internet of Things. I want to show this next slide. This is from Beecham Research, and it's a pretty old picture already, but it's a very nice figure showing the wide variety of different use cases that the Internet of Things can basically mean. So now the text is a bit too small for me, so I will just check a bit here. Okay, so there are different colors representing the different segments. You have building automation, you have industrial IoT, you have utilities, we have healthcare, consumer and home use cases. So IoT could be any of these things, and then you see in the figure how they split into smaller and smaller sub-segments. And in the outer part of the circle, we have one representation of the very core use cases that basically this can mean. So this is a nice figure just showing the big variety of things that when we talk about IoT, we talk about everything pretty much. I want to show, kind of make this more simple for you. So then we have some key technology choices that we need to make when we are working with IoT. So I think the first question to think about when you're wanting to do an IoT solution is to think about why to connect. So what are you connecting and why? So what do you want to gain from connecting something? So you want insights to data typically, and then you also need to think about where will you store the data and where will you work on it. So this is kind of the cloud part of things typically. Of course, it's very important to also think about what are you actually connecting? What is the physical device? Do you need to measure something there to get that data that you want? Is it a sensor? Is it sensing? Or is it an actuator? Do you want to have an action happen based on some criteria? Or is it something bigger? What is an IoT device actually? Is it a temperature sensor? But what if the temperature sensor is in a robot? Is the whole robot, the bigger entity, actually an IoT device? So these kind of things become relevant. Then the last thing is, of course, important to think about how to connect. So are you going to connect the thing over a wire? Or is it more sensible to go for a wireless solution? What kind of protocol stack will your device have? And what kind of stack do you have on the other end, in the cloud end? And how much data and how often is transmitted between the two endpoints? Today, since we're talking about 5G, our focus will be then on wireless connectivity with 5G. And that's where we are going to go next. Right, wireless connectivity for IoT. So in Ericsson, we have a tradition of releasing the Ericsson Mobility Report every year. And the latest one came out, let's see, now I have the wrong reference there. It should say November 2019, but it seems the link is to the January version. Right, but anyway, this report gives some predictions and shows data about what kind of connections are out there. And we have also tracked the IoT connections. So here we can see kind of an evolution of the IoT landscape. And if you look at the bottom part of the graph, we have the fixed phones in the very bottom. Those are the yellow bars. Then we have the mobile phones. And then we have the PC, laptop, and tablet type of devices. And you can see they are growing a bit when we go forward, but not that much. But then the purple bars, they are growing much more. And those are the IoT devices. So the biggest chunk of IoT devices is short-range IoT. And then the smaller chunk is wide area. So this means devices that need to communicate over long distances, and short range, of course, that they communicate over a short distance. Let's look next a little bit more into the cellular IoT connectivity growth. So this is now from our November mobility report. And you have the links there on the slides for later use. Here we can see a more zoomed in view into the cellular side. So basically we have three different types of uses. We have the legacy devices that use 2G or 3G. And that one is still growing a bit, but it's quite stable now. Then we have the massive IoT part, and that's the 4G-enabled IoT connectivity, something called narrowband IoT and Cat-M, so category machine, I think that refers to. And that one you see is growing quite a lot. And then the new use cases that come with 5G and also with 4G are the broadband IoT and critical IoT, and those are the more futuristic use cases. Okay, so now that 5G deployments are being rolled out and have been rolled out, we can discuss a bit what is there actually to enable these IoT use cases. And this picture is here just to kind of remind us that when we are starting with 5G, typically the first use cases are still the more traditional ones, which will be deployed at the moment. So we have the enhanced mobile broadband use cases and the fixed wireless access for residential areas, for example. And these are the typical use cases we see in the first deployments of 5G. And also the first devices are consumer devices. There are wireless routers and there are mobile phones. Then we have the machine type communication use cases, and that's what we're going to discuss next. This is a little bit older picture I have for requirements for 5G use cases. We have been dividing this space into 3 segments. In the next slide, I will split it into 4, so just to make it a bit more interesting. But on a high level, I think this still applies, so I wanted to keep it here. So we have the massive machine type communication on the left side. This means low cost, low energy, small data volumes, massive numbers of devices. These type of use cases, and as discussed, this is enabled already by 4G. Then we have the enhanced mobile broadband use cases. So this refers to use cases that are typical for home, enterprise, venues, AR, VR, for example, broadcasting, kind of smartphones, all these kind of use cases that have similar traffic characteristics to the mobile broadband use. That's the middle part. And that can be enabled both with 4G and 5G. And then we have the critical MTC. And this is something new for 5G then, on the right-hand side. And there we talk about ultra-reliable, very low latency, very high availability use cases. Some examples are industrial automation control, traffic safety, smart manufacturing, and so on. So now we split the space into 3, and next we split it into 4. So now then at Ericsson we have worked a bit more on this split, and we realized that actually the critical IoT, there is even one more category there. So we now have the massive IoT, the broadband IoT, the critical IoT, and then we have the industrial automation IoT. So the 3 first ones are the same as in the previous picture, and those were enabled by 5G. And this newest segment, industrial automation IoT, that's something that comes with 5G evolution. All right. You see here also kind of use cases with the colored dots next to them, referring to a bit what type of use cases are in this kind of industry that's listed here. And as you can see also on the left-hand side, 4G networks can enable the blue and the green use cases, so the massive IoT and broadband IoT, but then we're gonna need 5G and 5G evolution to go to the critical IoT and the industrial automation IoT. So there we need the 5G capabilities, basically. There's a white paper that came out some time ago, earlier this year, basically, so there's a link on the slide to that one as well. Let's have a look at an example, so a smart factory. So you can see all these use cases are present in this example. So first we have the massive IoT use cases, the blue ones. That could be, for example, inventory management and tracking and logistics. Then we have the green use case, that was the broadband IoT. And there we serve the videos, sensors, and cameras. Then we have the critical IoT, that was the orange one. And that, an example use case for that could be automated guided vehicles, so AGVs. And then the purple one, industrial automation IoT, that is something that, for example, collaborative robotics require. So this is an example of how a smart factory has different kinds of use cases, IoT use cases in the factory area, and each of them might need a different type of service. Okay, now we're going to go through the 4 different categories in a bit more detail on what they actually are. So first, we start with the blue one, the massive IoT. So with this slide, what I want to say is that massive IoT, it continues to evolve. We had the Cat-M and narrowband IoT in 4G already. They are still there, but they are still evolving for better coverage, better battery life, lower complexity, flexible deployment. This technology is 5G ready, and it can be deployed together with a 5G network. And the focus is on wide area. We're trying to enable this wide coverage, and it's applicable for all industries. And we have more than 120 commercial networks now in 40 markets that are enabling this technology. So it's already out there and can be used. Right, and then we can have a look at the different modes, or modems actually. So there are 2 different modem types in the market currently for these massive IoT use cases. There are single mode narrowband IoT use cases and dual mode modems that enable both Cat-M1 and narrowband IoT. So you can, as a user, you can choose which one to use. And in the table here, we have a bit of a comparison of how they differ. And the main difference is that if you have narrowband IoT only, so that's a less capable feature set, that's the most simple mode that we have, then we do not support, those devices do not support voice, and they don't support connected mode mobility. So if the device moves, you can, it has mobility but not in connected mode, and that's not actually needed because we don't have a voice service that would require continuity. And then final slide on the massive IoT is just to say that these are also part of 5G, and we can connect into a dual mode 5G core where we have the narrowband IoT and the LTE-M. And we can use dynamic spectrum sharing to share the resources between the NR and these LTE modes that are there. And there are a couple of references on the slide if you have an interest to dig deeper in this topic. Next, we're going to talk about the broadband IoT then. And this is something where we want to leverage the mobile broadband capabilities for IoT use. So as mentioned earlier, this is something that can be done with LTE already, but it's also, of course, available in NR. So what kind of use cases do we mean here? We discussed earlier the AGVs. Some other use cases could be, sorry, AGVs was critical IoT. I'm mixing things. Some use case examples here could be cooperative intelligent transport systems, utilities where we connect grid elements beyond meters, train networks, drones, advanced wearables, so these kind of smart watches with health monitors. And these use cases typically have multi-gigabit requirements for the data side, but still require quite low latency, lower latency than what can be offered with the massive MTC. And they require an uplink capacity, and that's also not possible with massive MTC. We still are in the wide area, and we still might want to have an extended battery life. So these are some use cases for the mobile broadband IoT segment. Okay, next we're going to go to the critical IoT. So this is where the AGVs were. Critical IoT for time-critical communications. So here the idea is that with critical IoT, we want to enable data delivery within a desired latency bound and with required guarantee levels. So the picture here shows that when you have the mobile broadband, in those use cases, we can have very low latency, but it's not guaranteed in any way. So actually the distribution of the latency has a very long tail. So you might have most of the use cases that have a low latency, but then you have a long tail of use case of packets that will experience a longer delay when they go through the network. This is called best effort, of course, and that's not acceptable for critical IoT. So shift to the right-hand side, you have the critical IoT, and there you can see we don't want to have this tail anymore, but instead we want to have a guarantee that 99.9% of the packets will be delivered by this deadline. As an example in the figure, we have the deadline at 30 milliseconds, and then 0.1% of the packets may experience a longer latency than that. So there is still a tail, but it's much smaller than in the best effort distribution. We've done some work then on evaluating what can we reach in 3GPP with the different releases of NR, of 5G. And the lower figure shows basically some results from there. So we can set different kind of reliability thresholds. It could be, so we need to choose the number of nines basically, and 6 nines is the most reliable mode of NR in release 16. So there we can see that only the green dot here, which represents release 16, can reach the 6 nines, the topmost row, and with release 15 we can reach the 5 nines reliability. So this is giving a picture of what can we actually reach. How is this low latency then enabled actually in the 5G network? So now we're going to look a little bit more into the details of the 5G protocol. And I'm just going to go over the different low latency features and high reliability features that we have. And there's a white paper also for this at Ericsson.com. There's a link on the slide to that if you want more info. But basically, one of the key features of NR as such is the numerology. So the NR physical layer is designed in a different way than the LTE, which enables lower latency. And this is done by having different options for subcarrier spacing that are different from LTE. And then we have with the slot duration scales with the subcarrier spacing. This is a basic thing. And then another thing is something called short transmissions. So in LTE, we had the subframe duration of 1 millisecond. But here in NR, we can actually have transmissions that are NR slots or sub-part of a slot, so mini slot. The shortest mini slot is 2 OFDM symbols, so that's very, very short, and that is another feature that enables the low latency in NR. Then we also have something for the uplink. It's something called grant-free transmissions. We can do, for the downlink, we can do semi-persistent scheduling, and for uplink, we can do something called configured grant, which is a feature where we basically offer the UE a grant in a configured manner, so it doesn't need to request the transmission. Then we have a feature more for the industrial side that's called preemption. And there we can basically, if we have a very high priority transmission, we can basically cut a lower priority transmission short and send the high priority data and then repair the lower priority transmission later on. High reliability features then, PDCP duplication is one important one, antenna techniques to enable this multi-user MIMO, and automatic repetitions. Then a big feature set that we've been working on in 3GPP is something called time-sensitive networking. And this is something that has actually been specified earlier for the wired Ethernet in IEEE 802.1. And now we are integrating this system into 5G to enable industrial automation. And this is exactly the purple part of the segments, so industrial automation IoT. There are different parts for TSN. Reliable deterministic flows should be enabled, and they should provide accurate time delivery for synchronization. Okay, I see we're a little bit running out of time, so I will speed up a bit. So there are some more features in NR on deterministic scheduling. Here is some explanation on how the uplink configured grant works, and then also on the downlink for semi-persistent scheduling. Let's not go through the details anymore, but we jump on to the industrial automation IoT, which a little bit was touched upon already there. So key features of this one are then real-time Ethernet integration, 5G TSN integration, and clock synchronization as a service. So these are kind of features that enable an industrial grade kind of service over the 5G system. So it's not only about low latency anymore, but we want to support these use cases that are out there in the factories, in the mines, in the construction yards, oil refineries. And they require a little bit more than the URLLC feature set that was in the critical IoT set. All right, then let's have a brief look at core network deployment options for critical IoT. So here I just want to show that we have different options depending on how the industry wants to deploy a network. And here we have shown 4 different options which have different level of integration into the mobile networks. So for the wide area, most of the functions can be centralized. And then we have the base stations out in the field. So we have the cloud models here as the white columns. So that's the rightmost side. Then we have different options to kind of centralize some of them or distribute them more into the field, or in the last option, have it in the local area. All the functions are on-prem. So this is kind of nice. 5G offers this flexibility. And as a final thing, before moving into the examples, I also want to mention that the frequency bands that are supported by 5G NR, and we can support critical IoT in all these different frequency bands. There are some more details on the slide then. All right, then, as a final thing, we're going to use the last minutes on having a very brief look at some of the examples on how 5G could be used in different industries. So at Ericsson, we have done a lot of collaboration with different companies around the world and from different industries. So I will show 3 examples now. First one from the automotive and transport area, second one from manufacturing, and the third one from process industry. So the first one is a use case on intersection control. So here, the main requirements are that we need to have certain latency, certain reliability, and we have connected devices. And this was something that was demonstrated in the Asta Zero test facility in Sweden. We had 2 Volvo XC90 cars connected and 1 Volvo truck. And then there was a coordination application running in the cloud. And the point was to have the cars pass so that they don't crash, of course. There is a video available on YouTube, so you can search Ericsson plus Asta Zero, you'll find it, and you can have a look. Okay, the next example I have then is 5G NR for connected adaptive production. This is something we worked on with Fraunhofer IPT and MTU in Germany. This Blisk, it was called Blisk, and this blade shown in the picture, it's an airplane turbine. Those are very expensive. And when it goes under this testing, it goes through very rough processes. And there has been a problem that sometimes the parts start vibrating too much, and then it basically breaks. So if we could detect the vibration early enough and stop the process, we can save a lot of money because the part doesn't break because of the testing process. So this is what we did with the wireless 5G sensor. A wired sensor doesn't work here because the part is rotating all the time and it's under these different fluids and everything. So, and this was a very successful new type of use case that can only be enabled with 5G and ultra-reliable latency communication. The final example I have then is the Kankberg gold mine. This is something we did in north of Sweden together with Boliden and Epiroc, ABB, Volvo and Telia. And here we deployed a private LTE network into the mine, into the gold mine. And there we have tested all kinds of different use cases, classical mobile broadband, voice and data service, also this remote control of the trucks. And there are also videos on this online, and there's some more material. Very interesting use case for 5G as well. That concludes my presentation on 5G and IoT today. So then I think I want to thank you for your attention, and we can move on to any questions that there might be. Okay, so the first question is, how many IoT simultaneously connected devices do we need to start talking about massive MTC approximately? Thanks a lot for the question. It's a great question, and it's difficult to say. I mean, I think massive MTC more refers to the kind of design of the system. So the point is that we can support a large number of these type of devices. We have designed the system to have capacity for a massive number of devices. It's difficult to say any numbers right now. I haven't looked into that for a while. So let's just say it's a lot. People have talked about and we should define the question better, I guess. Is it per cell or per, world or what? But people talk about billions of devices, and that's pretty much also what we are expecting to see in the field. The next question, will Ericsson market share shift from personal usage purpose to industrial purpose in the near future? This is another great question. And I think the answer is that, of course, Ericsson is very interested in the industrial market and the industrial use cases. And we have done a lot of work to prepare our 5G technology for those use cases. So hopefully we will see deployments, and we already have some deployments in fact. But at the current time, of course, the number of industrial purpose networks that have been deployed, it's much, much smaller than the number of kind of the mobile network operator networks that are the more typical use case for our technology and the legacy use case. Okay, and the last question, what are the major challenges Ericsson has noted in aligning 5G with IoT needs? Right. I think this is a great question as well. So as I went through the IoT modes, I think that gives you a kind of a hint on what have we noted around aligning 5G with IoT. Really, I mean, IoT use cases have been in the center focus when designing 5G, already from the physical layer design. So kind of enabling this very low latency, enabling the high reliability, those have been some of the key aspects that have been taken into account. So really 5G is IoT ready. Okay, and I see there was a final question. Did we have time to take that still? Yeah. So the final question is, does low-band 5G have significant benefits over traditional LTE networks in underground environments in terms of penetration through thick ground layers? The Kankberg case is extremely interesting. This is a very good question. Thanks for that. If you can just go back to the question, maybe. Yeah. So I have to say now this is actually an area that I don't have the full expertise in. So how far does the 5G signal reach in the same frequency as an LTE signal? So I need to check that offline and come back. Please send an email with this question to me if you still are interested in the answer later. But I would expect actually the coverage is very similar. That would be my guess, but without having looked into the details of the coverage question in NR. Okay, thanks a lot for your attention, and thanks for the opportunity to present here. So I wish you all a good day.
Thank you so much, Anna, for your lecture. So if you have any questions still for Anna, please send them to us via email and we will forward them to Anna. Next up, in a few hours, we are going to have the first pitching round. And now you have good time to finish up your presentations and prepare to pitch them. Thank you. See you in a few hours.